Okay, let's talk about the integrability of continuous functions and then of monotone functions. And I should say something before we get too much further into integrability. The book, we're doing just Riemann integration in these videos. The book does Riemann-Stieltjes integration, and it's sort of analogous to just taking a regular average versus a weighted average. In Riemann integration, all of the points in the function have sort of the same weight or the same density. In Stieltjes integration, we have a weight function or a density function that affect how sort of heavy those rectangles are when we're adding them up. And if you're having trouble with the alphas in the book, which are those weight functions, just treat all of the alphas as the identity function, sort of alpha of x equals x, or just replace all the alphas with x's if they're not written as a function. So, for instance, Theorem 6.5, which we're going to use today, says that the lower integral from a to b f d alpha, that's my weight function, is less than or equal to the upper integral from a to b of f d alpha. Well, if we don't like the Stieltjes stuff, we can just think of this as the lower integral from a to b f dx is less than the lower integral from a to b, or upper integral from a to b of f dx. This weight function, it's sort of nice sometimes. You can take weighted averages that way, but for this course I just want to deal with the regular sort of weights where everything is weighted the same. Okay, so Theorem 6.5 says this. I think I'm going to leave that as an exercise for you guys to prove. Also 6.6 I want to leave as an exercise for you guys, and it says f is Riemann integrable if and only if given epsilon bigger than 0, there is a partition and this partition works for both the upper sum and the lower sum, where the upper integral on that partition of f minus the lower integral of that partition on f is less than epsilon. Right. So 6.5, well, we've already proven that the uppers are bigger than the lowers, so this is a positive number, and so it could actually be equal to 0, but I can find a single partition that makes the upper integral and the lower integral close together, and sort of that's going to be useful to us in proving when things are integrable. So it's integrable if I can do that, and if I can do that, it's integrable. I'll have you also prove this as an exercise. So 6.5 and 6.6 will be homework exercises for you guys. Alright, so let's prove a theorem. This is 6.8. If f mapping a to b into R is continuous, then f is integrable. Okay, so let's prove this. So we're going to let epsilon be bigger than 0. What we eventually want to find is we want to find a partition that makes the upper integral and the lower integral less than epsilon, so we can use Theorem 6.6, which we had just stated. Okay, so set, we're going to use uniform continuity, so we're going to set delta bigger than 0 so that b minus a times delta is less than epsilon. Now, I don't want to confuse delta with the input, so let's say eta. We want to choose eta greater than 0 so that b minus a times eta is less than epsilon. Alright. Let delta be bigger than 0 so that whenever x minus y in absolute value is less than delta, f of x minus f of y in absolute value is less than eta. Okay, so there's where uniform continuity comes in. Right, it's continuous, AB is compact, so it's uniform continuous. We can do this. Then choose a partition P where delta x sub I, which is x sub I plus 1 minus x sub I, is less than delta for all I. I can do that. I can just take as many points as I want and throw them in there. If I have an interval bigger than delta, I'll throw another point in there and make it half as small. I'll throw a point in between the two endpoints of the interval and make it half as small. If I'm still bigger than delta, I can keep doing that. Just throw in more points until you have a partition that's sort of fine enough. Some of the terminology you might see in other books would be the gauge of the partition is smaller than delta. Okay. Then I want to show that m sub I minus m sub I is less than eta. Okay, why is that? Since for any x in x sub I comma x sub I plus 1 or y in there, f of x sub I, or f of x minus f of y is less than eta. So the difference between the maximum and the minimum inside that interval is also less than eta. Okay. And that kind of gives us everything we need. So let's look at UP F minus L P F. That's equal to, well, I've got the sum over I equals 1 to n from the partition, say 0 to n minus 1 from the partition. I've got the delta x sub I, and I've got mi minus mi. Okay. So the capital MI's are the upper, the little mi's are the lower. When I take the difference, I get the difference between the upper and lower. And this is less than the sum from I equals 0 to n minus 1 of eta delta xi, which is equal to eta. I can factor out sum from I equals 0 to n minus 1 delta xi equals eta times b minus a, which we chose to be less than epsilon. So by what was it, 6.6, the integral exists. All right. So if it's a continuous function, it's integrable. That's kind of a good key theorem to have. And now let's do it with monotone functions. Monotone functions aren't necessarily continuous. We can have jumps up or jumps down depending on which direction you're monotone in, but we still have continuity. Well, we sort of have continuity. Something we haven't proved is monotone functions are continuous everywhere except for a countable number of points, but really what the difference is I've got everything kind of increasing, so I can make my gauge of my partition, I'll use that terminology again, small enough that the difference between the low point in the interval and the high point in the interval doesn't get too big. So this is going to be 6.9 if f is monotonic on AB, f is integrable on AB. Okay. So let's prove this. All right. Let epsilon be given. For any n we're going to let the partition be the set of points that are equidistant apart from A to B. So I'm going to choose A, and I'm going to choose A plus 1 times B minus A over N, and then A plus 2 times B minus A over N. Right, so this is the distance from B to A divided into N pieces. I'm going to start at A, I'm going to take 1 step of that size, and I'm going to take 2 steps of that size, and so on. A plus N minus 1 times B minus A over N, and then B. So let me draw a number line here. Here's A, here's B. If I break this up into N equal pieces, then I've taken 1 step of B minus A over N, here's a second step of B minus A over N, and so on. Just kind of like a number line, fraction bar type thing. And I eventually, after I've taken N steps, I get all the way back to B. Okay, that's going to be our partition, P sub N. And we're going to just increase N until it gives us what we need, or the upper and the lower are close enough together as N increases. Okay. Alright, let's assume we've got monotonically increasing. Monotonically decreasing is very similar. We just have to flip which side the max is on and which side the min is on. So m sub I is equal to f of x sub I plus 1, and little m sub I is equal to f of x sub I, right? So the minimums on the left-hand side, the maximums on the right-hand side by monotonicity. Okay. Then the upper with P sub n as my partition, and f minus the lower with P sub n as my partition with f is equal to the sum of, well, I've got f of x sub I plus 1 minus f of x sub I times b minus a over n from I equals 0 to n minus 1. Right? Each of the intervals is the same width, the maximum and the minimum. And that's equal to, well, b minus a over n can factor out front, and that summation telescopes, and so it's equal to f of b minus f of a. The middle ones cancel each other out. The endpoints don't get to cancel out, so I've got this sort of telescoping series again, or telescoping partial sum, and I end up with this value. We can find n large enough I should probably be using a capital N here. Capital N, capital N, capital N. We can find n large enough so that b minus a times f of b minus f of a over n is less than epsilon, which gives the desired partition to show integrability. Using 6.6 again. Okay, so there's two theorems. We've got continuous functions are integrable and monotonic functions are integrable. In the next video, I'm going to go through a couple examples of how we actually compute integrals using some of these limits, and we'll see that there.